during the talk.
This meeting is being recorded.
Then please type it in the chat. I will monitor the chat and I will interrupt Klaus to say there is a question in the chat and I will read the question. So don't be shy. Start to write the question in the chat and I will interrupt the talk immediately. Okay, otherwise we have about 60 minutes plus discussion time. So I will monitor the time that is spent on the talks, on the questions during the talk, and then subtract that from the 30 minutes afterwards. And I will now have the pleasure to introduce today's speaker. This is Professor Klaus Werner from the University of Nantes. Klaus is actually an old friend of mine. I will tell you briefly when we met the first time, but let me first say that he received his PhD from the Technical University of Munich on a thesis entitled Nucleon Transfer in Peripheral Heavy Ion Reactions. And after he received this PhD thesis in 1984, I should say, he became a postdoc, first at Heidelberg, and then he went to Brookhaven National Lab for actually 3 years, I think. No, sorry, more years. 6 years, 5 years, 5 years. Huh? About 5 years. Yeah, yeah, but you became assistant physicist, a staff assistant physicist also then in Brookhaven.
Yes.
Yeah. So all in all, you spent 3 years. Sorry, I forgot the postdoc in Heidelberg. 3 years, and that is actually where we met. I think at one of these Brookhaven summer schools, and I think also Peter Koch was still there as a postdoc, and I guess Uli. I think Uli was also there during this time. I don't know whether he visited or he was also postdoc there. No? I guess, yeah, and maybe David Vasak also. I forgot. Maybe he was there also. But anyway, after that he became an associate at CERN for 2 years, I think, 1 or 2 years, and then again spent some time in Heidelberg as a postdoc, where he also received his, or where he did his habilitation on a thesis entitled Strings, Pomerons, and the Venus Model of Hadronic Interactions at Ultra-Relativistic Energies. And shortly after that, he also became a Heisenberg stipendiat, spent some time there still at Heidelberg, but in 1995 he became a professor of physics, first second and premier class, and then later class exceptionnelle 1 and class exceptionnelle 2. So from 1995 on, he has been at the University of Nantes, and we are very happy that he is here now today to tell us about heavy ion collisions from 5 TeV down to 4 GeV in the EPOS4 framework. Okay, Klaus, please take it away.
Okay, thank you very much for this kind introduction, which reminds me that I'm quite old since this thing is so long. And thank you very much for the organizers for giving me the chance to talk here. It's really a pleasure to do so. And this is actually my first talk ever about BES physics. And so the transparencies have really been done for this talk. That's not just recycling of old stuff, which is kind of rare. Usually one takes old things. Let me first of all mention a little bit the EPOS4 project in general before I then come to what's announced in the title. First of all, to say what we do not want to do. We do not want to just provide another model to study flow, but the idea is more to have a complete event generator which can do normal PP physics. So we are still interested in PP physics to start with, and just basic things like, for example, a model like PYSIA can do, like total cross-section, the light flavor spectra, jets and charm, and all kind of the normal PP physics, and which can do in addition, without completely changing the model, just the same model can do in addition collective effects in small systems, which is an interesting subject at the moment, and in addition can handle nuclear scatterings from LHC down to RHIC. So just to give you an idea of what we want to do, and then certainly we do not want to or we cannot kind of reproduce each single curve on a precision of 2%. That's not really the idea. So more we want to check if we get a consistent overall picture. And actually, EPOS4 exists since quite a while, but there was not a single official release of the code for good reasons, because there are always something missing. And so finally, we kind of, I think, solved the basic problem, and then it was EPOS4. And there we have the first official release in October 2022. So now we have a dedicated web page, and to present was I already explained the general purpose approach, which is completely public and explains how to use it, and testable. So contrary to the EPOS4 stuff, which was more something private. And it has been tested a lot by myself, because it should really treat all systems. So this took quite a while, from 4 GeV up to 13 TeV, from PP to lead for light and heavy flavor, for collective stuff, and for hardening. So the idea is we cannot yet really look at everything, but this is the aim. So and many things I really checked by myself. So the aim was, first of all, to release the code so that people can use it and we get some feedback. And the papers are a little bit coming after that. So they slowly arrive. So the first one has been published, at least it's on the archive for the moment. And soon there will be a version 2, kind of improved version. And 2 more papers are more or less ready. So there are more papers coming about the whole project, because there are many details. So Annie will talk, of course, about a very small kind of fraction application of this vast project. And there are some work in progress since the EPOS4 was kind of the basis, considered the basis for other things, which now develop quite actively. So there's a project at Nantes, which is called EPOS4 plus heavy quarks. So it's heavy flavor physics with my colleagues from Nantes. And also we have a second project, which is EPOS4 plus jets. And finally, this is still based on EPOS4. Might be interesting for this community here. This is an EPOS4 plus PhD, where we discussed a little bit hydro versus transport, but this is for the moment at 200 GeV. Maybe it would be interesting to extend this to lower energies. This is just to give you some idea of what the things are we are working on. Okay, so now I come to my talk. And first of all, what I'm going to tell you, the first thing I want to discuss is some very elementary discussion about parallel and sequential scattering. And so the question here is, what kind of model do we need for a given energy? And in the energy range from a couple of GeV, of course, we do not want to go beyond, up to, in principle, up to infinity. So it's more the question what kind of data exists. So that's why I talked about 13 TeV. So this is kind of the maximum we get at the moment. Then I think I will convince you that this parallel scattering stuff is really an important thing. And I will talk about the parallel scattering in EPOS4. This is a little bit theoretical, although I'm aware that this is not a theory workshop. So I try to be as little technical as possible, but a little bit I need to do nevertheless. Then, once this is done, we will talk about really the physics when we change the energy. So the role about core and corona and remnants for different energies. So the different sources of particle production at different energies. So how physics changes as a function of energy. So this was essentially the aim of this project. And then in the fourth chapter, I will discuss results. And here, essentially, it's a question comparing simulation with data to see essentially how well it works. It's not really the aim to discuss each curve in detail, but more do we get an overall agreement, because there are always several components which play a role, which I will discuss in the parts before. Okay, so this is what I want to do. So let me start with the first part, which concerns parallel and sequential scattering in heavy ion collisions. And here on the right-hand side, there's a sketch of a heavy ion collision. So you see the z-axis, which is a longitudinal axis, so along the beam, and the time t. And we have two nuclei which collide, and this is the space-time picture. And just to simplify things, I take three blue lines, which represent three nucleons in each of the two nuclei. The points, the black points, these are possible interactions, assuming that the trajectory are close in transverse direction. So that's just a sketch of a heavy ion collision in space-time. And from this plot, you see there are three fundamental time scales which are important. So one is the T collision, which is the duration of the complete collision. The next one is the T interaction, which is the time between two nucleon-nucleon interactions. So it's the time between two of these black dots on the plot. And then this has to be compared with the formation time, the T form, which is a hadron formation time after the interaction of two nucleons. And all these times are considered in the center of mass of the system. So for simplicity, I consider two symmetric nuclei, and I work in the center of mass system of the two. Now, one can relatively easily define low energy and high energy. So low energy, that means where we can apply sequential collisions or cascade simply. And here the condition is that the formation time is less than the interaction time. So in this picture here, so we have I don't know if one can see my pointer. Yes, I think so. So here we have one of these blue lines, which makes the collision with a blue line from the other nucleus. And then we have an interaction at this black point. And then particles are produced. And then if the formation time is short, then the particles are produced immediately. And then they continue to make interactions. And so the secondary kind of particles, they start to make interactions immediately. Okay, and this is what I would call low energy. And there we have another extreme, which I will call high energy. And here we simply have to look at the longitudinal size of each of the two nuclei. So I look at a symmetric system. And here the diameter is 2 times the radius divided by the gamma factor. And if this is much smaller than 1 Fermi, then all interactions are simultaneous. If it's really much smaller than 1 Fermi over C, then I can consider this interaction area as kind of instantaneously, and all interactions happen at t equals 0. So if I look at the plot on the right-hand side, I mean, we still have all these interactions, and we have all these possible interaction points, but all this area here is essentially point-like, but the interactions, nevertheless, they happen, all of them. And here, necessarily, one needs to treat all the interactions instantaneously, and the particle production is a second step. And here we have also a condition, and here the condition is that the formation time of particle production should be bigger than the total collision time of the two nuclei. And in this way, we can kind of compute to two thresholds, what means really high energy and low energy in my language. Now, low energy and high energy nuclear scattering is really very, very different, and different theoretical methods are needed. So at high energy, one can completely separate primary interaction at t equals 0 and secondary interactions, which is then all this equilibration and hydroevolution and so on and so on. At low energies, of course, this is not so easily doable anymore. So the high energy approach is then there's an important thing. It's not just the initial condition. There's an important dynamics. This is parallel primary interaction. So this is kind of the elementary thing when it comes to high energy nuclear scattering. So and now to be more precise, I want to give some numbers. What means high and low energy? Now the energy is in the sense of this square root S of the nuclear-nucleon interactions. And then high energy threshold is defined by the formation time equal the collision time. So everything beyond is considered high energy. And this low energy threshold, ELE, this is the formation time less than the interaction time. And everything below that, I consider low energy in my language. Now, to do some numerical estimates, it's a little some basic stuff. Let's assume for simplicity we have a formation time of 1 Fermi over C to make some things simple. And the high energy threshold, which means the T formation is equal to T collision, which means 1 Fermi over C is equal to 2R divided by gamma times the velocity. And I take a big nucleus with 6.5 Fermi, and then we get from this equation gamma times V over C is equal to 13. And then it's easy exercise to get out the energy for 1 nucleon, which is 12. And then we get the energy of the nuclear-nucleon system, which is 24 GeV. So you see, quite elementary. I mean, it's just an estimate. So I will use these numbers, but of course it could be 30, it could be 15. It's an estimate, of course. Then the low energy threshold, it's almost the same calculation. So now we have a T formation is equal to T interaction. And again, I take the 1 Fermi over C. And now for the interaction time, we have, again, the 2 times the radius, but divided by n. And n is the number of nucleons in a row. So this is a kind of the additional thing, divided by gamma times V. And for the n, that's the new thing here. I just make a simple x estimate. I take the nuclear density and I take the cross section. I take a cross section of 40 millibarns at relatively low energies, and this gives me an estimate of n roughly 7. And then the calculations gives gamma times V over C, which is 2R over N over 1 Fermi, which gives 13 divided by 7. And then from this, you get quite close to 2 GeV. And this is again the energy for 1 nucleon, and the energy for a nuclear-nucleon system in its center of mass is 4 GeV. So now we have 2 numbers at least, which I'm going to use. And I think it's quite useful, even though they are just rough estimates. So we have the low energy below 4, we have the high energy above 24, and we have, well, we have something in between. And this intermediate range is kind of difficult. So we need actually partially a parallel approach. So we have something which I sketch here on the right-hand side. So we have again the initial nucleons, the blue lines, which make a first interaction, and then still a second interaction may be possible. But then at some stage, the particle production will start before really the 2 nuclei went through each other. And so that means at this point, this nucleon here that will not exist anymore to continue to make the 3rd collision here, but instead we have
sorry to interrupt
several seconds.
Sorry to interrupt you. Yeah, Bernd had a question. Don't you need a factor gamma on the left-hand side also? I guess it's on the, it refers to the previous transparency. Bernd, can you comment?
Yeah, Klaus.
Yes.
When you have the projectile coming in and hitting the other nucleus, and gamma is defined in the center of mass frame.
Yes.
Then the projectile nucleon is also moving with a Lorentz factor of gamma, and so the formation time has to be multiplied by a factor gamma as well. Isn't it true?
Yes, that's true.
And so the other way to think about this is to say you go to the rest frame of the target, and then it is the gamma in a fixed target experiment, which is basically 2 gamma squared set of mass.
Yeah, so in principle, it's a little bit more complicated because for the produced particles, of course, it depends on their velocity as well, and one has to take into account gamma factors as well. That's true. Yeah.
Okay, so the energy threshold should be a little lower than 4 GeV. That's my argument.
Mm-hmm. So, I mean, it's really here, let's say, a rough estimate. And actually, for the formation time, it's then also a question of the velocity of the particle itself, not just kind of the nuclei. Anyway, so we have two thresholds, which I would say are around 4, are around 25 from this estimate. And let's say in between, this is kind of the complicated thing. So we need to kind of a mixture between the two. So that's not a fully parallel picture, and it's not a full cascade either, but a mixture of both. And this, I will come to back to this at the very end when we look how well things work and or not work. Now, coming to proton-proton, here the discussion is a little bit different, but it's also a question of gamma factors. So, I mean, here in proton-proton scattering, it's a high energy thing, and at high energy thing, an interaction starts with an emission of parton cascade. And here also we have gamma factors. And so the first emitted partons, they have a high speed, and you have big gamma factors for them. So they are long-lived particles. So if you have a very high energy collision, then the lifetime of these things is very big. And simply because of that, and it's many, many Fermi, so it really takes a long time to develop the whole thing. And therefore, to have something like two interactions of this type, one after the other, is simply completely impossible. And so from this reason, and for a little bit different arguments, but again, based on gamma, we can see that also for multiple scattering of partons and proton-proton scattering, we need this parallel scattering scheme. So we have parallel scattering at high energies for multiple partonic scattering, and we have this multiple parallel scattering also for nuclear collisions. So which brings me to this landscape here of what kind of approach as a function of the energy and the mass number. So when I start with proton-proton, multiple scattering only exists at high energy, so there's no point to go at low energies. And therefore, everything is parallel. If we go to heavy ions in the upper part here, then according to my estimates here, we go down to 24 GeV for this parallel approach. Then we have this partial parallel approach, and then we have the cascade. The important point is, even taking into account that the estimates are not very precise, but the kind of this low energy thing where we need parallel scatterings goes well into the RHIC domain. It goes well into this BES energy scan domain. Okay, now let me discuss a little bit of this parallel scattering scenario. And I will start with, I know you are more interested in the low energy end, but I will start with high energy but for good reasons. I mean, the point is the high energy case contains in principle everything. And when we go down in energy, we do not need to add features. We simply see that certain phenomena simply die out when we reduce energy and automatically. I do not have to do anything for that. And also we start with PP, and because it's impossible to construct the AA approach here in this formalism without first to understand the PP. And then this is probably unique in this approach. The PP going to AA is really trivial, which is not really trivial usually. If you want, let's say, consider a general approach and not just, let's say, hard probes or something like that, but generally a generalized PP to AA. It's not really a trivial thing. And now the message from my first discussion is essentially that high energy starts actually relatively early, whenever the gamma factors start playing a role. So at a few certainly at a few GeV already. And therefore, I think it's useful to
interrupt once more. Sorry.
Yes.
So Wenbin has a question. He says the transition collision energy from high to intermediate energy is roughly 24 GeV, and that's close to the 19.6 GeV where one has various non-monotonic signals. And he asks whether this is a coincidence or whether there is some physics behind this. I don't know whether this is the right place to discuss. We can postpone this question maybe to the end, or when it's okay for you.
I think it's good to postpone this question to the end, because I will come to that exactly when I discuss really the physics. Okay. Okay. Now let's start. And these are really very few technical things which I have to discuss, but I have to, otherwise I cannot explain what EPOS4 is about. So it's a very compact summary. And the start is the elastic T matrix for PP scattering. And if you want to have more details, it's actually the Fourier transform with respect to the transverse momentum exchange. So it's in impact parameter space where we working at. And the main point is that this scattering T matrix is supposed to be a product of elementary T matrices, which each of them represents the parton-parton scattering. And at this point, it's already clear that it's completely trivial to go from PP to AA, because we still have a product of many T matrices, but simply we have many T matrices per nucleon pair. So we just have more parallel T matrices, and we have more integrals, but in principle, nothing changes fundamentally when we go from PP to AA. Then, of course, we are not interested in elastic scattering. It's just to set up things, because all the rest is then essentially a consequence. And the connection to inelastic is given by the optical theorem and so-called cutting rules. And then the cross-section is then the sum of the product of so-called cut pomerons. And the cut pomeron is a squared inelastic amplitudes, which at the end of the day ends up as two kinky strings. So that's a very, very short summary of what we are doing. And the plot, which corresponds to that, is shown here. And the two colored boxes, these are my cut pomerons, and they are the fundamental building blocks of the whole thing. And they are clearly, you can see they are parallel. So we have here the x1, x2. These are momentum fractions of the external legs of the parton-parton scattering, and all the rest, all this parton PQCD stuff is inside these boxes. So it's well hidden for the moment. So the approach is very, let's say, modular. So these elementary interactions are modules, and all the PQCD stuff is inside. Then there is a major problem, and it took us really many years to first understand and then find a solution. And I think the easiest is to explain this for nuclear scatterings with a nuclear modification factor, which probably everybody knows. For example, you look at something as a function of PT, and then the RAA is the AA result divided by the number of collisions times the PP result. And this should be unity for hard probes without finite state interactions, or in PA, where we don't expect these interactions. So what we would expect, for example, for PT, high PT particles, as a function of PT, would expect that this RAA goes to 1. And one observes this, so that goes to 1. But in the model, it does not. Unless you really do things properly, which we didn't know how to do so far. So, for example, in EPOS LHC, which is very much used at the LHC, this thing didn't work. And this is not just a little problem. That's really, in principle, a model killer. So if this doesn't work, that means the whole model doesn't work. And therefore, we spent really a lot of effort on trying to understand that. And it's actually not so difficult at the end, once you understood, to understand where the problem is coming from. The problem is coming from the fact that if you look at these pomerons and you look at the nucleus collision, like in my sketch here on the plot on the right hand side, so I have a nucleon and a projectile I and a nucleon J, and I have an interaction between the two, which is then represented by our cut pomeron. And now if we have energy sharing, the complete energy which is available, which is in the nucleons initially, has to go to the pomerons and then go to particle production in the second step. And now if we have many other pomerons which kind of connected to the same line, then of course we have energy sharing. And to quantify this, we first define some variable which we call n-con, which is connection number, where we count the number of pomerons connected to the same projectile and to the same target, and then we divide by 2. So this number is the number of red and blue dots in this plot. And then it's clear where n equal 1 means an isolated pomeron, and bigger than 1 means there are many concurrents for the energy, and the energy has to be shared. When you talk about the energy, a useful variable is the x plus times x minus. of the external legs of the pomeron, which is the same thing as the S, the Mandelstam S of the pomeron divided by S total, which means it's the energy squared divided by the energy squared of the total collision. And X equal 1 means that one partial collision gets the whole energy. Now, if we look at the distribution of this quantity, this determines everything else. So it's kind of the mother distribution of everything. It determines the petit distribution of partons and everything else. And so first of all, we look at the X distribution itself. And if we do this on the plot on the right side on the bottom, here we have the reference curve in red, which is just for one pomeron, and what we get when we have more which share the energy, then of course we get a deformation. What we say, we get a reduction at high X and we get an increase of low X, and this is very clearly, I mean, you cannot avoid that. That's simply energy sharing. The energy needs to be shared, so a single pomeron cannot get the full energy if it as it would get if it would be alone. Okay, so once we understand that, we can try to parameterize that. So we define a deformation of this distribution, which is a function of the number of connections relative to the reference one, which is this R. And this is just the ratio of these two curves on the bottom. So it's a dashed curve divided by the red curve. And this is what we see here on the plot. And what we now the point is, which is very important here, we are able to parameterize the deformation beforehand. And it's an iterative process. We have to do it several times. But then we can kind of use the parameterization, which are the black dots in the plot here. Then we make the full simulation. Then we compute after the full simulation this deformation function, and we get the same thing out. So which means this deformation is under control. Now, the second thing which we need to do, we need to do now the link to QCD. And the QCD are the parton ladders. So we, for the moment, we have our building blocks, which are these G's, which are the cut pomerons. On the other hand, we can compute GQCD, which is based on perturbative QCD. And we do that. And we actually, this depends on the X plus, the X minus, on the Mandelstam S, and on the impact parameter B, but in addition, it depends on the cutoff Q squared, which is normally just a cutoff, but for us, it's an important variable. So we can consider this as a variable. Then we compute, that's really a big project. We compute all these things in a very efficient way. We tabulate things, and then it's accessible via interpolation. So which means the QCD G is available. And now we can define our box. So our black box G, we can say what it is precisely now for each cut pomeron for a given X plus and a given S and a given B and a given connection number. We postulate that our G is given as 1 over the deformation times some normalization constant times this GQCD, which depends, and this is most important now, which depends on Q sat. And now on the left-hand side, this is independent of this n-con, so it doesn't depend on the environment, but the right-hand side depends on that, but it depends on that the things cancel out. And so the Q sat now is kind of takes over all this deformation to some extent. So this depends heavily on the connection number. And this, one can prove that. So that's the first time we can really kind of mathematical proof that this will work for high energies up to infinity, that actually this problem of the energy sharing does only affect the low PT via a saturation scale, which is really absolutely crucial here, which suppresses low PT, but it doesn't suppress high PT. So the high PT part is kind of safe, and when safe are the RAA problem. And the only thing what it does, it affects low PT things. So this was really after a long time and many attempts, kind of the solution of the problem. And so that's all. So that was kind of my very brief summary of the theoretical part of the EPOS4. Now I will come to the next part where I want to show how things change when we go to low energy. So that's maybe the thing which you're interested in most. And again, I start from the high energy because, as I said before, going from high energy to low energy, things simply get simpler, things die out. So this is now a concrete thing how our diagram looks like with our cut pomerons, which are now precisely parton ladders. And I think I don't need to discuss this more in detail. But anyhow, the important thing is that we have the remnants, and they play a very important role. The remnants are always white. So there are no strings between the remnants and the hard processes like they construct in PYSIA. So the remnants are completely white. But they can have kind of strange flavors content, so they are not necessarily UUD. So you may have S quarks or whatever inside, but they are color white, and they are excited. So they may have high excitation, and they produce what we call, first of all, prehadrons. And that's much more than resonance excitation. It's more like high mass diffraction or something like that. Then we have the Pomeron ends. These are always QQ bar pairs, or more generally 3-3 bar color representations. And these are the ends for this parton cascades. And then we simply follow color flow. It's a very strict kind of algorithm following color flow to construct kinky strings. That's a one-to-one correspondence. And so at the end of the day, these things here are translated into kinky strings. And then the kinky strings decay, and then we get prehadrons, and the kinks, they may hide PT things, so we get jets in this way. So everything is in here. So this is for soft and for high, for hard processes. Now, this is the high energy thing, and we are not interested in jets here, I think, but we are interested in what happens when we go down in energy. When we go down in energy, first of all, the partonic stuff gets less energetic. So the high PTs things get less PT. They get shorter. So the total energy per kind of cut pomeron gets smaller. And finally, the hard pomerons disappear simply. At very low energies, there are no hard process anymore. They get purely soft, but this is absolutely no problem. So simply the kinky strings get flat strings. So at very low energies, we have simply still the same thing. We have still this interaction, but we have flat strings, and we have no hard process anymore. Or they are rare. They are always there, but they get so rare that in normal processes they don't play a role. Okay. But the point is now the remnants are getting more and more important relatively. So not absolutely, but relatively, because from the middle there's less particle production, and therefore from the ends, of course, this is more important because also they are getting more into the center. Then we have the core corona procedure. We take all this prehadrons, which I discussed here, and we have some procedure for a given prehadron to move out, which based on its velocity to moving out of this bulk, and based on an energy loss, where we assume some simple parameterized formula of the energy loss per unit length, which is proportional to the density of this objects. And then if the energy loss is bigger than the total energy, then we call this a core prehadron. If the energy is less, then it's the energy loss is less than energy, and it's a corona prehadron. The corona prehadrons can get out, then they are promoted to hadrons, and the core hadrons, they make the core. And the corona procedure, I can show what this really gives then. And first, well, I do this very briefly for PP. It's already something important for PP. So I show here the number of prehadrons as a function of the space-time rapidity, which more or less the same thing as rapidity. So you imagine this rapidity. I show all prehadrons. I show the core prehadrons. I show the prehadrons from remnant decay, and I show the core remnant particles. And you see for the high energies, there is essentially everything is dominated by the pomerons from the middle. The remnants are much less important. And nevertheless, this is minimum bias proton-proton, but the core is even important there. And this, when we go down in energy, well, at 2.76 is more or less the same thing. Then we go further down at 200. Still, the core is important, so we cannot fit the data at 200 GeV proton-proton without that. And you see already at lower energies, the remnant part is moving to the middle, and it plays an important role at central rapidities as well. And finally, at low energies, there are no pomerons anymore, and there's no core anymore. And the same thing for heavy ions, and no surprise. So what I show here is again, as a function of the space-time rapidity, the number of pre-hadrons, for again the different things. And for lead on the upper left plot, you see that the points and the line are identical, which means the core is essentially everything. So everything is core, everything is finally going into the hydro part. And the remnants are less important. Then if we go to gold, and with increasing energy, first of all, the core gets less important in the fragmentation region at large rapidities. And the remnants are getting more and more important. You see already, if we go to 27 or to 19 GeV, then the remnant part dominates already everything. So the part which is coming from the internal part, from the hormones, is kind of less important. But this remnant part is really very important. And maybe surprisingly, this dominance of the core goes down till the end, till 7. And then it drops completely. So at 4, there's simply no core anymore. Then, well, time moves on fast. So maybe I skip that and go right away to this one here, which is we compute the energy density now for the different systems. I mean, we want to do hydro afterwards, depending on the energy density initially. So we have some start time tau 0, and the start time is a parameter, and which affects the spectra. So and here in practice we have something which goes from 1 Fermi over C for the lead to 2 Fermi over C for the gold star at low energies. Now what we do, we compute the T mu nu from the pre-hadrons. Then we boost to co-moving frame, which is defined such that the T mu nu, the first column of the T mu nu has just the first component, and the kind of the space component are 0. That's the definition of the co-moving frame, and that allows us to compute the energy density and the flow vector. And this is then finally plugged into the initial condition for hydro. But already based on this, what I show you is the energy density as a function of the radius. So that's a space variable, the radius in terms of Fermi for the different system. Then and also plot here the freeze-out energy density, which is 0.57 GeV over Fermi cubed. And you see, I mean, for lead, you are way above. So we have high energy densities. Then it goes slowly down, and for me it was a little bit surprising if I go down in energy from 200, 60, 39, 19, 15, 40, 14, 11. It goes down really very slowly, and then it jumps. So below 11, so here at the end, it goes very quickly. So then the energy density goes down very quickly, and it's getting very close to at least to my definition of the freeze-out point. The next step is then hydrodynamic evolution. Here we use the same code since a long time from Yuri. And then the sudden freeze out where we do microcanonical, and then hadronic cascade with UrQMD. So this is the same thing which we do since 10 years. A short remark, because this might interest you, about the equation of state. So what we did at the time, we just made something up which essentially works well for mu equals 0, which is just a superposition of a kind of an equation of state for a hadron gas and equation of state for ideal plasma, and then the parameters to make a superposition of the two are fixed to kind of fit the lattice data. And the result is shown here. On the right-hand side, you have the epsilon over t to the 4 without units as a function of t in GeV. And here our result is the red curve, and the points are the lattice results. And then I have to admit we just made something up for mu different 0, because at the time it was not really the thing we were looking into, but that's what we get. So this is the green curve here, which is used still at the moment. Then, and this was part of the PhD thesis of Maria Stefaniak to check out the best equation of state. And this is the dashed line here for the same mu b equal 450. You see, it's kind of different just by accident. At the freeze out point, the two are identical. But of course, we do not use much of the equation of state, but for the hydroevolution, of course, it counts. And so I plot here the dp over the epsilon. for the EPOS equation of state at mu equals 0, and red the EPOS equation of state for mu equals 450 in green, and the best thing dashed for the best equation of state for 450 as a dashed curve. And that's actually at the higher values of t, it's not such a big difference for all of them, but there's a big difference at low t. Now, the particle spectra, again, is part of Maria's PhD thesis. We do not see any difference, but it could be that it's due to the fact that EPOS4 didn't work well for low energy. So now it works much better, and so we should look at this again. And also, we didn't go down really to very low energies where the thing is really maybe relevant. So there are some things to do. Now, some core corona plots to see how the different contributions contribute. So I plot in the following: the core plus corona, which is primary, plus core corona separation, plus hydrodynamic elution, plus microcanonic decay, but without hadronic rescattering. This is core plus corona. The B is the core, which is the same as A, but just looking at core particles. And the corona is the same as A, but just looking at corona particles. And the full is everything, which just means A plus rescattering. And then we get plots like this, which really summarize, I think, nicely what we get. So the different columns are the different centralities at a given collision. The different rows are different particles. So we have pions, kaons, protons, and lambdas. And the different curves, the green curve, so the yellow curve is just one. The green curve is core over core plus corona, so that's relative weight of the core. And the blue is relative weight of the corona. And well, the yellow is the sum of both. And the red is the effect of the rescattering. So if the red curve is 1, that means there's no effect. If the red curve is different from 1, there's an effect from hadronic rescattering. Now, you see, of course, at low energy, the core is dominant, at least for central collisions, and that is for all particles. If we go to more peripheral ones, then of course it's getting a little bit less extreme. But still, for the baryons, the core is always very dominant, even for peripheral ones. I mean, the baryons, they profit more from the core than the mesons. And here you can see what is maybe the most important quantity is the crossing. So the crossing means where we get the dominance core towards the dominance of the corona. And you see, I mean, it's here around maybe 4, and then it's going to smaller values for peripheral up to 2. And for the baryons, it's bigger. So for the baryons, it's maybe already 5 or 6. The transition from core to corona area. So this is one thing important to keep in mind. And then you can see the importance of the hadronic rescattering, which is quite big already for kaons, protons, and lambdas. So we see that reduces particles at low PT and gives some increase at high PT. So the rescattering concerns interactions between core and corona particles, just to be clear. So this gives you a summary how things look like. And I think I should go fast. I think the important point is if we go to lower energies, the picture doesn't change much, which was a little bit surprising to me. At least for central collisions, it doesn't change too much. The most drastic thing is, of course, the high PT disappears, which is well, very natural. And in addition, the effect, of course, of the rescattering, which increases. So you see, on the low end side, and also I have to distinguish between particles and antiparticles at low energies. So here we have protons and antiprotons, and you see already here a difference between the protons and the antiprotons. There's a big suppression of antiprotons, and if we really go even more down in energy, then still the core corona picture doesn't change so much. But the rescattering changes a lot. So if you look at the left plot here, you see an enormous suppression of antibaryons and due to baryon-antibaryon annihilations in the hadronic cascade part. So the hadronic cascade part is always important at all energies, but even more at low energies, not very surprisingly. But both components are important. So it's first of all, the core corona plays an important role, and then the hadronic rescattering. And so what did we learn? So the core corona picture using the same prescription does not change too much from 4 TeV down to 11 GeV. A little bit surprising for me. I thought that the corona the core part would go down, but it's not really the case. The core dominates at, well, obviously dominates at intermediate. Well, I didn't really say that, but I should have said actually this green curve, the core, has not a minimum at PT equals 0, which one might think, but at intermediate values of PT, which is still coming from flow. So the flow pushes things up to intermediate values of PT, and therefore we get typically always this kind of maximum situation at intermediate values of PT, which is a clear signal of flow. The core dominates at intermediate PT and at all energies, actually, maybe even stronger at low energies, which is a sign of strong radial flow at all energies down to the lowest energies. The nevertheless, hadronic cascade, so I think this is certainly very important, but nevertheless, hadronic cascade gets increasingly important towards lower energies. And then below 11, kind of core disappears very quickly. Now I have 10 minutes left, I think, if I'm right.
13 minutes. 13.
13.
13, yes.
Yes. Okay, so that's, I think that should be fine. Coming to results, and I would like to make a systematic check going from very high energies down to 7 MeV. And the best analysis and simulation is essentially the kind of analysis of the simulation data, and the data collection is part of the PhD series of Johannes Jean. And here we do a systematic check now from 7 GeV down through all the best energies which exist, down to 7.7 more, not MeV, GeV, of course. Then we check if the concepts discussed in the previous chapters give a coherent picture and reproduce the data. The aim is not to discuss each single curve in detail. I mean, I think the main point of the chapter before was essentially to discuss the physics, and here we essentially want to see how well things work and when they work well or when they do not work at all. So this kind of stuff. And shown here are only PT spectra, only a very small selection, because I will not show 200 plots here, and checked as well, because otherwise it wouldn't make sense, but not shown here are flow harmonics. So I concentrate on the PT spectra, which already have a lot of information, and usually people kind of for a little bit the flow stuff, but I think one should look at the PT spectra as well. You also can learn things from that. Everything are log plots, and but they are really, I try to make it really such that you can see 10 to 20% deviations, and we are not more precise than that. So this is not an approach, a general approach where we can kind of have 2% precision for all the kind of fits we are looking at. Always the colored lines are EPOS4, and the black dots are data. Okay. And actually, papers with more complete selections, they will appear first on our webpage and in papers. So maybe I just skip. Well, we checked many let things, but since this is not the main interest, I maybe continue to start with the gold stuff. And I more or less show you always very similar things. I show you pions, then I show you always not yet here protons and antiprotons for the next one, and then the hyperons. They are also quite interesting, like lambda, anti-lambda. So here in this graph, I have from the left to the right PT spectra of pi plus, pi minus, K short, lambda, anti-lambda, Xi bar, and omega plus anti-omega. And the different curves are corresponding to different centralities. And the axis, if I hope you can see this, this are PT values from 0 to 6 here, and from 0 to 5 for the hyperons. Now, if you look back to the core corona pictures for the pions, there is some corona dominance at high PT. So the high PT stuff really needs kind of the hard part. Otherwise, this would not work. On the other hand, for everything else, for the baryons, the kind of the hard part is not important. So all this is coming from the corona part. from the core part. So this is really from things which are coming from the decay of the fluid. And here the fluid is pretty important. I mean, for this is for getting you need the flow for getting the hyperons correctly, the PT spectra for the different centralities, and also the total yields. You need two things. You need the flow, and you need the statistical hadronization. So in our case, it's microcanonical, but this is not really the most important thing. But the statistical hadronization, this is a crucial thing. In addition, important is the rescattering, which makes kind of a reduction at low PT of a factor of 2. So these three things are equally important. So the flow, statistical hadronization, and the rescattering. So you cannot say this is just one or the other. So everything is important. We included many more things. So I really have hundreds and hundreds of plots for 200 GeV, including all kinds of V2, V3, V4 stuff. In general, actually, gold 200 looks pretty good. So I think it looks the best compared to all energies we are looking at. Actually, it seems to be the easiest one. I mean, at higher energies, we have to worry about the hard stuff and all that, which is not so important here. So to some extent, this is kind of the easiest part, and it's very stable. So we always get relatively good results. Going down in energies to 39, and now we see always the same plots. So you see here from the left to the right, PT spectra of pi plus, pi minus, proton, antiproton, lambda, anti-lambda, xi, anti-xi, and for many different centralities. It's always the most central is the upper one, and the most peripheral is the lowest. And well, here everything is, at least for the upper parts, for the more central one, everything is core dominated. So the corona part doesn't play an important role. And it's also useful to look at the hyperons always, because they depend even more than the other ones on the statistical hadronization and the flow, and this seems to work pretty well. Overall, I would still consider this at reasonable agreement with the data, although there's a little bit excess. But as I said, that's we cannot have a precision for everything, but the overall picture looks kind of reasonable. So again, we have additional checks. We also checked V2s, and so I would still, it's a question of definition. I would still say that looks okay. 727, the same thing. So all the same. It looks almost like the 39. The hyperons on the right look pretty good. The pions look pretty good. The most difficult are the protons and antiprotons. Well, here the protons are still quite good. Antiprotons are a little bit high. But overall, still 27 look reasonably good. And then we go to 19.6, and then you see still the pions and the hyperons, they change a little bit, but slightly still reasonable. You see more kind of changes concerning always the proton and the antiproton. So these are kind of the things which are most difficult to reproduce. So here we have a little excess of antiprotons. Well, I let you decide what you think, if it's still acceptable or not. But here at 11, I think there one can see very clearly, and again, you see it for all. So here you see already for the pions on the left-hand side, they are too steep. And also for the hyperons, the same thing. They are kind of too soft to be more clear. So actually all spectra are too soft, and it's always kind of the best seen for the protons and the antiprotons. And here you see very clearly that first of all, they get too steep, they get too soft, and there are too many for the central ones in particular. There are too many. But for kind of concerning the shape and the fact that things are getting too steep, it's essentially for all centralities. So for 11.4, we start having problems, and I can really assure you we tried the best kind of to have it's not a question of parameters, so you cannot do really better than that. And the Next thing is then at 7, and then you see that things really get bad. So here for the protons, antiprotons, there are way too many proton antiprotons, and in all cases, kind of the spectra are really much too soft. So there's here something going wrong at low energies, and it's nothing you can do about that within the approach we have. And we really tried, but there's nothing to do. So what do we learn here again? So it seems that the model works reasonably well down to roughly 19.7. Of course, it's a question of discussion if this still works well or not so well. But anyhow, at some energy around this, things seem to work. And then if you go to low energies, it fails increasingly. And it fails completely at 7.7. So it looks a little bit that something goes wrong, but first of all, it's not completely wrong, but finally it really goes wrong. And well, fortunately, this was not really designed so that it fits, but it fits quite well what we discussed in the very beginning concerning our different scenarios. So we use, for all what I show you, we use the parallel scenario, which means if we have the two collisions, then in principle, this nucleon, which makes A and B, would continue to make C, collision number C. That's what we do. But that's not realistic because after B, particle production starts, and which means the remnant which I use here, which makes the collision C, simply does not exist. And therefore, we have too many of these things here, and this should be changed. So I think, and in principle, it's something which is straightforward to do. But this should be done, and therefore, it's maybe not very surprising that the model doesn't work. To some extent, it's a good situation. So from a theoretical point of view, the model should not work, and from a practical point of view, the model does not work. That it's relatively clear what we have to do from our side to fix that and to see if we can go down a little bit further in energy, which is, I think, interesting also from what I showed you before about the equation of state, where it would be nice to go as far as possible down in energy, even if the core part is relatively short-lived. So for me, it looks a little bit similar to what we know from small systems. The plasma part will be short-lived but nevertheless interesting. And I come to my summary. So the S-matrix approach looks like a natural tool to implement rigorously parallel scattering as done in EPOS4. And it should be used actually beyond something like 24 GeV. And there are long-standing problems, and I just want to mention that there's no real EPOS paper since 2013, because I was always sure that there's some serious problem which we didn't find a solution for. And there are no official releases of EPOS4. And what is used mainly by the proton-proton community is EPOS LHC from 2012. And so I think these long-standing problems which are related to the energy sharing, which ruins factorization, which finally ruins the model, they could be fixed. It doesn't mean that everything now is perfect. There are still many things which can be questioned, but the fundamental problem has been solved, and this is a good basis to continue. And so in principle, at least, we can now attack low and high PT phenomena equally well. So it's not a low PT, it's not a high PT model. So in principle, both are accessible. Then what I showed you, there seemed to be a very smooth transition from high to low energy. Well, I think as always in physics, so things usually do not happen too drastically. So the physics changes very little, at least down to 20 GeV. Maybe the statement is no longer true below. And up to then, our approach works reasonably well. And then things really go bad. So below 20 GeV, the parallel scattering, well, the model fails. And I think that's the parallel scattering which is the reason for that. And this partial parallel scattering should be implemented. So in principle, straightforward to do, and definitely needed if we want to go down in energy, which I think is an interesting thing to do. Now, below 4 GeV, there's certainly no point to use EPOS4. Even in improved version, there will be no it looks like, of course, it's based on a model which is not perfectly, let's say, right at this low energies, but here there is no core anymore. So therefore, running EPOS is the same thing as running hadronic cascades, so you can do it right away. And that's essentially all I wanted to say. So thank you very much for your attendance.
Thank you, Klaus, for this exciting talk, which will raise many questions. Actually, let me ask the first one, or maybe make a comment. If you look at your DPDE plot, which you have implemented now at finite baryon density, it looked like you're missing a bit of there. It was there. It looks like you're missing a push from the high baryon density region. And
yes,
maybe could push the protons to higher PT, and also since they don't sit that long anymore, it would make them harder. So maybe your proton antiproton spectra could be solved by just implementing the best EOS. Okay, but that's probably a comment. And so before you give up on the parallel scattering or fully parallel scattering or no partial, yeah. And maybe that is an easy thing to fix first. Okay, so sorry. So we still have one question by Wen Bin, which you promised to answer, and then I see questions by Hui Chao and Bernd. So Wen Bin,
could you repeat?
Yeah, I repeat the question. So there is so the 24 GeV was your transitional collision energy, and that's close to the 19.6, where many non-monotonic signals appear. And the question of Wen Bin was whether this is an accident or a coincidence or some physics behind that.
Well, I would guess, I cannot really say much about that, but it looks to me as well that at that point really physics changes. I mean, in my case, it's a question of first of this parallel and non-parallel scattering stuff, but this changes already kind of the basis of all the rest. So I would really think that here's a real transition where physics changes. From this is in my model, so maybe many different reasons, but in my model or in our model, things really change at this point from this approach which I showed you today, where actually nothing really changed from the construction of the model. But if we would do this kind of partially parallel scattering things, then really we need put in something which could have pretty drastic changes.
Mm-hmm. Okay, I guess no follow-up from Wen Bin. So let's take the next question by Hui Chao.
So EPOS can also be implemented to air shower simulation for cosmic rays, right?
Yes.
My question is, comparing with such heavy-ion collision or its collider modes, what kind of special feature you should consider for such air shower simulation?
I'm not sure to got all the points. So what particular features you mean about air showers?
Yeah, I mean that I think I read some of the paper that implement EPOS to air shower simulation. My question is, comparing with the traditional heavy-ion collisions, is there any special feature one should consider to include it in EPOS in such air shower simulation, or you implement the same EPOS for both air shower simulation for cosmic rays and heavy-ion collisions?
We do take the same thing, but let's say before doing so at the moment, I think we should not do that. The idea is, of course, that we take the normal model. So that's the idea, that we test the model for a collider with collider experiments, and then we plug it into air shower stuff. On the other hand, in air shower things, there are very special things which are important, which have to be checked. So usually when we check things, let's say when we're interested in heavy ion collisions, these are not the things which are important for for air showers. So, for example, what is very important for air showers are things related to diffractive scattering and very forward particle production. So all these things, they need to be checked. So it's not so much that we need a different model, but we have to look at different observables in addition, which we did not do yet. So the point is, this is one of the projects for the next year, that we kind of look at these things in particular to be sure that the model can be used properly for air showers.
Okay, then the other question is, for example, we have different hydrodynamic models. If one insert such hydrodynamic models for the air shower simulation, what do you think? For example, EPOS, what is the advantage for EPOS compared with other hydro simulation for air shower?
Well, first of all, you cannot use hydro in air shower simulation because it's simply not doable because of the CPU time. So what one needs to do, what we did already, and this is also something which we will do with EPOS4, you need kind of a parameterization of the hydro part, kind of based on parameterized flow. So you parameterize essentially the outcome of hydro, because otherwise it's simply not possible. And the point is what we hope. I mean, if you know about cosmic ray things, there's this muon problem, and one of the ideas that the muon problem can be solved by a quark-gluon plasma, but this should be then at forward region. So kind of the hydro part should be important. We hope that the hydro part will be important, but it should be important even at the forward region. And but then you need to do something that's more a technical problem. So you need to provide something to these people which is really fast. So you cannot really do full hydro calculations during the simulation of air shower.
Okay, thank you. Thank you.
Okay, the next question is by Bernd.
So, Klaus, thank you. That was very impressive stuff that you guys have put together, and the agreement at high energies is also very impressive. I have two things. Number one, I just briefly wanted to expand on the question or comment that I made in the beginning of your talk, and then ask my question. So expanding on this, I think really when you go to the low energy domain, it's more easily analyzed conceptually in the target rest frame. And when you do that, you find that the simple hadronic cascade, in the sense of not taking into account formation time in some not fully understood way, requires that the center of mass energy is well below 3 GeV. And so already at 4, you're running into serious issues there, which leaves the real challenge for the field to come up with a credible and consistent model in the range from that lower energy to, say, 24 or 30 GeV, which we don't have at the moment. I don't think hadronic cascade are sufficient for that, but I don't think we have a model that actually covers this in a consistent fashion. So that's a big challenge. The question that I have is concerning your way of treating the multiple Pomeron interactions. And here it's really, in a sense, a question. In the 90s, in the mid-90s, when the color glass condensate picture was first proposed, there was a debate in the field about whether saturation is an initial state phenomenon that really can be analyzed in the target nucleus itself, as Larry McLaren and Raju Venugopalan proposed, and also L. Müller had worked on. And the other one was that it's really more a final state effect, in the sense that the particle production processes quench themselves because they take energy from each other. And I think the community decided ultimately that it was primarily an initial state effect, that it could be probed easily in electron nucleus conditions as well, and it's universal in that sense. How does your picture fit into this? Is it really similar, an initial state saturation effect, or is it a final state, or is it none of the above?
No, it's absolutely initial state. let's say the pomerons are really a very simple concept of a Diglab ladder, so completely linear, and we know that this is wrong. So in principle, you should replace, if you really would like to make a microscopic calculation, then of course you need to replace this by something where you have kind of ladders which make fusion and all that, which happens at the end of the ladders. So you should modify this, and what we do is kind of just an effective way of taking into account all that, what would happen at the end of the ladder. So it's definitely an initial state effect. And it is something.
It looks like, but in the pictures, it looks like something that happens during the collision and not before the collision.
No. The point is with this, I think it's probably the best to look at this picture, which I showed in the very beginning here. So when we look at the interaction, and this is just a simple one, and just an elastic one, so cut it in the middle to have an inelastic one. So it takes a long time to prepare. And so in practice, let's say, even if the interaction time is very small, but at LHC energies, the total time of this process may be 100 Fermi. So it takes an enormous amount of time to develop all that. And therefore, if we have a fusion of two of this kind of ladders, they both are prepared a long time in advance. So there's no point that this can happen during the interaction. So all this is something which has happened a long time before.
Okay, thank you.
Mm-hmm. So I see 3 more questions in the chat, and I will read them. The first is by Vitaly Osvenchuk. Can EPOS4 be used to study P-bar P and P-bar A systems, in particular at SPS energies?
In principle, yes. Well, in practice, one has always to check if it works, but in principle, yes.
Okay.
If somebody is interested to use it, so we have now a help email, so just try it out, and if it doesn't work, contact us.
Okay. I hope Vitaly is happy. Okay, I will read the next question by Yuka Kanakubo. It's related to the ongoing work you mentioned at the beginning, EPOS3 plus PHSD. Are you using PHSD initial conditions in EPOS at this particular work? I would be happy if you could tell us a little bit more about if it is possible.
Yes, if I get the time from the chairman, I'm happy to say something.
Okay, well, there's still one more question, so that so maybe 15 minutes or so, but okay.
Oh, perfect. Because I know you have your deadline in 30 minutes.
In 15 minutes.
So what we do in this work with PHSD, so we compare 3 different things. So the first thing is we take the initial condition from EPOS, and then we take the evolution from PHSD. And in parallel, we compare this with the full PHSD. Well, it's the initial condition from PHSD and the full PHSD and the evolution of PHSD. And we take the well, I think essentially this point is interesting. So in this way we can kind of distinguish between initial condition and final state. So in practice, the answer to the question essentially is that we try several things. So we try to take the initial condition from EPOS, and of course we take the EPOS complete, so EPOS initial condition plus EPOS final to compare with the EPOS initial condition plus PHSD evolution and compare to the pure PHSD. So you see we have 3 different scenarios with different combinations of the initial conditions and the evolution. Well, that's quite interesting to see what are the difference. And there are quite big differences.
Thank you. I'm looking forward to the results. Thank you.
Okay. Very good. So then finally, Yang Zhang, he says, hi, Klaus, I have 2 questions. One is about heavy flavor production. Did you check the production of charm coax? And the second, okay, let's maybe answer that first and I read the second question.
Yes, that's an important thing. I mean, since we now can do hard probes as well properly, so one of the most important things is to look at charm production. So we check first of all spectra for charm things, and now we also look at really charm in heavy ions. So which is this EPOS plus heavy quark project. So the charm stuff is an important thing now for our activities.
Mm-hmm. Okay, I think Jan is happy. But let me also read his second question. It's about the deformation. So if he wants to simulate a new system, what does he need to know about the new system to do the deformation?
The point is we need in reality we need some iterations to determine this deformation. This depends on the energy, and it depends on the system. So when we have a new, and at the end, at some stage, we need to parameterize all that, but we are not yet there. So for the moment, we need one table for each system. So if you are interested in a new system, then we usually take the system which is the closest, and then we make a couple of iterations to kind of find out what is really the optimal deformation. So this thing finally converges. And then we put this into some table, and then this can be used till we make a next update with new parameters. I mean, the point is it's getting a little bit more heavy compared to what we did before. In principle, let's say if we make a big upgrade and we have many new parameters, then we have always to check all these tables so that they are still okay. And in the worst case, we need to spend some time to kind of also make these tables again. So which in principle require kind of iterative procedure. But of course, we want to give you the program such that it works. It just makes it difficult for the user directly to change something that's a little bit more complex then, because one has then to update the tables. But again, we are usually, if you send an email to EPOS4, then we answer immediately. If you have a new system you're interested, we will provide you with the tables which are needed, so you don't need to worry about that.
Excellent. So Jan says, thank you for the answers. Okay. I don't see any further questions in the chat, and I also don't see any further raised hands, but maybe wait for a few seconds. Maybe somebody else would like to ask a question. If not, I think let's thank Klaus for this exciting talk and new information. And I guess this is then the end. Hui Chao, please help me if I should do something else, but I guess we're at the end so far.
Yeah, I think no. Maybe see you next week.
Yeah, then see you soon next week, and have a nice afternoon.
Thank you very much for your attendance. It was a pleasure. Bye-bye.
Okay.
Thank you. Bye-bye.
Ciao. Bye-bye.
Bye, Klaus. Have a good day.
Bye-bye.